So welcome everyone to our fourth seminar of the course. We're very happy to welcome Marta Ortin to this seminar. She's going to give us an awesome talk. I think I've already listened to her a few times on this topic. Marta is one of the co-founders of the startup Dive Medical, and which is a spin-off of a startup of the University of Zaragoza that focuses on the application of eye tracking and artificial intelligence to diagnosing visual pathologies. And she, as an in-house researcher, she completed her PhD at our university a few years ago. She has made internships in Intel and in mobile communications and the Korean Advanced Institute of Science and Technology in South Korea, and also at the University of Ferrara. Just so you get a grasp on what this new startup she's going to be talking about today means, this startup has drawn the attention of Huawei technologies, and I think that they just started a new project with them. She's going to be talking about this company on this talk, so whenever you're ready, you're free to.
Okay, thank you very much. I think, are you seeing my screen, full screen now?
Yeah.
Yeah, okay, perfect. So yeah, as Julio already introduced, thank you very much. What I'm going to talk to you about is Dive, which is now a startup, but it began about 7 years ago as a research project. So this started as a collaboration among engineers from the University of Zaragoza, specifically the Graphics and Imaging Lab, and ophthalmologists and opticians at the Miguel Servet Hospital. And it started about 7 years ago, and after working on it for a few years, we started realizing, and other people starting telling us that we had maybe come up with something that could be useful for other people. So we had a device able to detect visual pathologies and to examine vision that could be useful for other people besides us within our research group. So that's when we started playing around with the idea of founding a startup and finding out the way of how we could transfer this technology to society. So that has finally become a reality. This year in February 2020, we finally founded the startup, and it has lived for only a few months, but only in this short period of time, it has already achieved quite a few huge milestones. For example, we have just closed our first investment round with quite fat players investing in us in this investment round. So, for example, we have Banco Sabadell investing in our company. We have been selected out of 146 candidates to be invested in by Banco Sabadell. And we also have an investor group from Harvard investing in us. And as Julio said, we are now running our second project with Huawei, in collaboration with Huawei. So what I'm going to talk to you about is a bit the journey we have followed to get to where we are now, because I think it was 8 years ago or so, I was standing exactly where you are right now. So I was doing a master's at the University of Zaragoza, and now we have achieved all this. We have co-founded this startup that has so much potential. So yeah, this is a bit what I'm going to talk to you guys about. So let's start from the very beginning. All this project started from a problem. So there are right now in the world more than 2 billion people with vision impairment. And if we focus only on children, there are more than 800 million children with visual problems. The most striking fact is that actually 70 to 80% of those cases could have been prevented or treated if they had been detected early enough. But the problem is that this early detection is not that easy. And that is because it's a huge challenge for ophthalmologists to explore vision in young children because they cannot communicate with them. So they are, we call them non-collaborative patients because you cannot ask them questions, they cannot answer back to you, they cannot read letters out of posters like adults do. So these non-collaborative patients are babies, they are very young children, they are even people people with neurocognitive disorders who cannot communicate. So the way vision is explored in those patients is like what you can see here. So the ophthalmologist sits in front of the child, for example, and presents them with several stimuli. So then the ophthalmologist needs to figure out how the child sees based on their behavior when presented with those stimuli. So in order to do this properly, the ophthalmologist needs a lot of experience. And even when having all that experience, explorations are very subjective. They are not very accurate. They're not repeatable. They take a lot of time. So this makes it very difficult to come up with an early diagnosis. And not having an early diagnosis for a baby or for a child when they have a visual problem, it may affect not only their visual system, but also their general development, their education, and their socialization. So in order to solve this problem, we have developed a device called DIVE. DIVE stands for Device for an Integral Visual Examination. And it looks like what you can see here. It presents several stimuli on a screen, and it allows us to perform a fast and accurate exploration of the visual function, even in these non-collaborative patients. So in order to make DIVE work, it is based on two main concepts. So the first concept is illustrated by this image here. So I'm showing this to you. I haven't given you any explanation, any instruction, nothing. And I'm sure, I'm positive, all of you and all of us, we are all looking at the turtle. We're all looking at the turtle because that's what's different, that's what stands out, and that's what humans do. So this is called preferential looking. And all humans, we are all wired to do this, to look at what's different, what moves, what stands out. And we have been programmed to work like this after thousands of years of evolution. And even babies, since the moment they're born, they work like this. So we all look at what's different. And that's one of the things we use in order to implement our tests in our device. The second thing we're based on is eye tracking. So I'm sure you've heard of it, or maybe some of you have even tried it. So what eye tracking allows us to do is it tells us, or it allows us to know with very high precision the point in the screen the user is looking at. So it starts with a calibration process, and after that, it knows exactly where we're looking on the screen. And it works the following way. So you see this is a sample image in which you can see a device that is located underneath the screen. So this device shoots infrared light towards the eye of the patient. This light is harmless, and the infrared light reflects on the eye of the patient or user, whoever is sitting in front of it. And then it has a camera to capture an image of the eyes or the face of the person, of the user. And so it computes the, let's say, shape of the reflection of the infrared light on the eye of the patient. And based on the shape of that reflection, it is able to figure out at which point of the screen you're looking at. So based on those two things, we're able to build our device and to design our tests. So now putting all this together, this is what DIVE looks like. So you can see the device on the left-hand side of the screen, and you can see how it is being used by a child. So the device is presenting different stimuli on the screen. These stimuli, they may seem like naive, silly drawings, but they are actually carefully designed to test the different aspects of the visual function. So the child simply needs to sit in front of the device, and just as if he was watching TV, he doesn't need to do anything else, doesn't need to receive any instructions. And while this is happening, the eye tracking system is collecting all the gaze information from the child, so that you can get a better intuition about why this works. Let me show you an example. So let's imagine this is one of the tests our DIVE device includes. So it's a bee appearing and disappearing in different parts of the screen. And I can show you here with the red dots. The red dots are representing the gaze of the child that was performing the test. So in this case, the red dots correspond to the gaze of a child with normal visual development. And you can see that the dots or the gaze that the patient was fixating on a very small area on top of each bee, and it was moving very fast and very accurately from one bee to the next. But now let's compare this to the gaze of the child with abnormal visual development. You can see the gaze is much more erratic. This child was not able to fixate on a small area on top of the bee. He could not move as fast or as accurately from one bee to the next. So from all these gaze patterns, we can extract a lot of information and a lot of metrics that the ophthalmologist can then use in order to make an early diagnosis. Okay, so far I've explained to you the basics of the problem we're trying to use and the basics of our dive device and how it works. Now I'm going to go a little bit more in depth into the design of one of the tests that we have developed and that are running in Dive, and that is the color perception test. So first of all, let me tell you that the proper medical name for color perception problems and color perception deficiencies is actually not daltonism. The proper name for color perception deficiencies is dyschromatopsia. And there are several types of dyschromatopsia, and daltonism simply corresponds to one of those types. So I'm showing you in here an image of parrots with all sorts of colors, red, blue, green, yellow, all sorts of colors. And now I'm adding below 3 more images. These images show how people with each type of dyschromatopsia would see the image that you have above. And the way these color perception problems work is the following, or the reason why they exist. So in our eye, we have photoreceptor cells that are called cones. And these cones are classified into 3 groups. So there's a set of cones dedicated to the detection of green color, a set of cones dedicated to the detection of red color, and a set of cones dedicated to the detection of blue color. So depending on the type of cones that you are missing or that you have faulty, then you have one type of dyschromatopsia or another. So you can have deutan, protan, or tritan dyschromatopsia. And the most common ones are deutan and protan. You can see they actually manifest on a very similar way. So those 2 images at the bottom are very similar, but they are due to different biological a different biological reason, which, as I've just told you before. And tritan is the least common one. And these dyschromatopsias in general, they happen to 80% of men and 1% of women. So right now, dyschromatopsias are tested with a test like this. This test is very widely used. I'm sure you've seen it before. It is the Ishihara color test. I was actually very recently tested with this at the doctor's office, so it is being used. This was developed more than 100 years ago, like the beginning of the 20th century, and it works the following way. So you can see there are several plates, and in each one of the plates there is a number hidden. So there's a color for the background and a color for the number. If the person is able to distinguish the 2 colors, he will be able to read out the number. If the person is not able to distinguish the 2 colors, then he will not be able to see anything at all. So this test has been widely used. It's still being used and it's fine, but it has several problems. The first problem it has is that, remember, we are talking about non-collaborative patients and babies. So this test cannot be used by a baby or a very young child because they cannot be asked a question, they cannot answer, they cannot read numbers, so they cannot use this test. Also, since it was developed such a long time ago, it was developed even before color theory had been developed. So this Mr. Ishihara, he did it by trial and error. So he just tested different color combinations. He drew different plates, different stimuli. He showed it to many different people. And when he found a color combination that a few people could not distinguish, then he thought, okay, I've got it. This is going to be one of my plates. So that's the way he developed it. And because remember, there are 3 types of dyschromatopsias. The 3-tan dyschromatopsia is not very common. So at the time, they didn't know it existed yet. And so Mr. Ishihara was not able to include plates that tested for 3-tan dyschromatopsia because they didn't know it was around, and they didn't find people who had it at the time. So this is the way this test works. Now I'm going to tell you how we designed the test. We didn't do it by trial and error. We actually based our test on modern color theory. So I'm going to base the explanation on the CIE color space. This is one of the multiple representations of color that are out there. And this specific representation allows us to graphically draw or graphically represent color perception on top of this diagram. And the horizontal and vertical axis, the X and Y, I'm not going to go into detail of what they mean because that's not relevant for us today. But you can see in this diagram all around the diagram, you can see we have all the different wavelengths of the visible spectrum, and in the middle of the graph are all the possible existing colors. So based on this color space, I'm going to explain this to you using the protan dyschromatopsia as an example. Okay, so remember there were 3. I'm going to use protan. First thing we can do is draw a point which is located at a specific coordinate. So this point is called copunctual point, and it is the point corresponding to the protan dyschromatopsia. Bear with me for a moment. You'll understand why this point is important in a second. So this point is located at a specific coordinate. These coordinates were discovered or found out after years of color perception theory. And from this copunctual point, we can draw lines that go through the color space. For example, we can draw this line. This line is called a confusion line. And what is interesting about this line is that we can take any 2 colors located on this line. So for example, we can take those 2 colors, and we know that these 2 colors are candidates to be confused by a person that has protan dyschromatopsia. So we use these 2 colors to build one of our stimulus. So we use one of them to paint the background, and we use the other one of them to paint the figure, the triangle in this case. So if the person is able to distinguish these 2 colors, they will be able to distinguish the triangle. And because it's different and it stands out, they will look at it, and we will detect they are looking using eye tracking. If they are not able to distinguish the 2 colors, then their gaze will just wander around the whole screen, not finding anything interesting enough to look at. And we will also detect that with eye tracking. So remember I told you we can draw lines, several lines from this point, a copunctual point. So we have many different confusion lines starting from this copunctual point. And remember, I also told you there are 3 types of dyschromatopsias. So we actually have 3 copunctual points and 3 sets of confusion lines. And so we can, based on this theory and the way color perception works, we can test very, very well the perception of our patient on the whole color space. And then there are also a couple of other interesting ideas that we use to build our stimuli. And Ishihara already noticed this and already used these tricks, but because they are very good, we keep using them. So the first one is, I'm sure you've noticed that both in Ishihara plates and in our stimuli, the background and the figure, they are not simply a smooth color. we build our plates using circles of different sizes. And that is because we need to avoid having a very clear edge between the figure and the background, because we don't want to give any additional clues that can help the person identify the figure. We want the person to identify the figure only if they are able to distinguish the colors. We don't want to give them any more hints or any additional help. Another thing that you may see is that again, both the background and the triangle, they are not built. They are not drawn with the exactly same color all around. We have a certain kind of noise. So what is going on here is that we are using the same chromaticity, but we are using different luminance. So this means we have darker circles and lighter circles. So let me show you with an example why this is relevant. In this first example, we have a gray background and a purple circle, a purple figure. And both the background and the circle have the same luminance all across. A person not able to distinguish the chromaticities in here would see this stimulus like this. So we see the same chromaticity everywhere, but we are still able to distinguish the shape because we notice it has different luminance than the background. So again, this is not what we want. We don't want people distinguishing the shape due to things different than the actual color. So when we include noise in the background, in the luminance, both in the background and in the shape, a person not able to distinguish the two chromaticities would see it like this. So the shape automatically becomes invisible. So those are the main concepts that went into building our color perception test. And when we put all that together, this is what the final test looks like. So we show different stimuli based on the color perception theory and the lines and copunctual points, confusion lines that I talked to you about before. And then what we can also do is we adapt to each patient in real time. So if we show them a color pair and he's able to distinguish the shape for that color pair, then we show them more complicated stimulus. So color pairs in which the colors are closer to each other, more similar to each other. And if they're not able to distinguish them, then we show them more complicated things. Sorry, if they are not able to distinguish the colors, we show them easier color pairs so that we end up finding the exact threshold for each patient. Okay, so until here, we've seen the problems ophthalmologists have and what we have done to solve the problems and help them explore vision in little children, in young children. But that's not all that we have to do. So this doesn't solve all the problem because there are many, many children that do not get to go to the ophthalmologist at all. If the only children that go to the ophthalmologist are those in which something has already been detected. They are children in which the pediatrician suspects they may have some problem with their eyesight. So the truth is that no visual screening is performed in children younger than 3 years old. And this is true even in developed countries, for example, in Spain, where we have a good health system and children regularly go to the pediatrician and there are established protocols to just check them out. Pediatricians do not perform a global visual screening for them just because they do not have the tools available that allow them to do that. And if we think of developing countries, then this problem becomes even more important and even more severe because in developing countries there's even more difficult access to ophthalmologists and to any specialist or any doctor in general. There are not enough specialists for the population So the World Health Organization has determined that visual screening programs are the best tool to reduce the prevalence of vision impairment. And in order to implement these visual screening programs, what we need to do is develop tools that can be used by anyone. So they can be used by pediatricians, but they can also be used by anyone from the community to identify which children have visual problems and then refer those children to the ophthalmologist or a specialist who can properly diagnose and treat them. So in order to do this, we started using deep learning and artificial intelligence. So this is where deep learning comes into play. Right now we are at a time in which all the governments in the world, they are considering artificial intelligence in general, or even deep learning in particular. They're considering it as key for the development of many areas of their country. And especially if we focus on the health sector, this is gaining an immense relevance. If you just Google AI health, you'll get millions of results, because this is right now the biggest advances are taking place in this area. And so a revolution is going on right now in the health sector when applying artificial intelligence and deep learning. So what we do is we incorporate deep learning into our Dive device, into what I explained to you so far, so that we can automatically analyze all these metrics, all these case patterns, and all this information that we capture. We can automatically analyze that and give back in real time the probability for the child or any patient to have normal or abnormal vision. And it was in order to develop this that we partnered up with Huawei. So what we needed was funding to develop our project. What Huawei needed was real stories and real projects that showed how their technology could be used. So they were launching this new smartphone called the P30 that includes a chip inside that is called the Kirin chipset. This chip is able to run AI algorithms, and they wanted stories and projects that could show people how this chip could be used and what it actually meant that their phones had this chip. And also they want to show how they give back to society, and they want to show that they are interested on helping society move forward, help people with less resources, this kind of thing. So they have a program that is called Tech for All, and in this program they are including a few projects related to health, to the environment, and I think to education as well. So we were part of this project, of this program within the health sector. And the project was called Tracker AI. And what you can see in this image here is the presentation, the launch of the P30 smartphone. And our project was showcased during this presentation. The person that you can see talking in here is Richard Yu. He's the CEO at Huawei. And it's actually, we didn't know until we got here, but it's actually a huge deal to be included in this presentation, and it is extremely competitive. So the way this works is the following. So this presentation happened in Paris in March 2019. So a few days before the presentation, all relevant people from Huawei, people involved in the launch of the P30, they all traveled to Huawei. And we were also, they all traveled to Paris. And we all were also flown to Paris, along with a lot of other people working in other projects with Huawei. And so just 2 days before this presentation took place, it was like an X factor of projects. So we all presented our projects to lots of Huawei employees, managers. We don't even know how many people we presented this to, even in hallways, corridors, everywhere. We just kept presenting the project. And yeah, there was a very tough selection process. And just 1 or 2 days before the presentation, the actual few projects that are going to be showcased during the presentation are selected, and then they work around the clock to prepare the final slides, final wording, final everything for this presentation. So yeah, it was quite competitive and quite an adventure to get here. And also one other secret that I'm going to let you guys on in. So this project, you can see it's Huawei and us, but actually at the very beginning, it was Huawei, Google, and us. But I'm sure you've heard it. In somewhat around May 2019, the US ban for Huawei happened. So then from one day to another, Google was out of the picture. So we stopped being involved with Google, and we kept collaborating only with Huawei. Okay, so I think now that you have all the gossip, we can go on to the actual technological side of things. Yeah, so this is the way our dive device with the screening module, this is the way it looks. So you can see the main difference that you can see here with respect to the previous video that I showed to you before is that now we have a smartphone here included in the equation. So the way this works is our dive device is running its different tests, and the technician doesn't have to be a doctor. The technician uses the smartphone to control the progress of the test. And when it has finished, when the screening has finished, it sends all the data it has collected, all the metrics computed with our gaze analysis algorithms and all that. It gets sent over to the smartphone that runs all that through our deep learning model, and it produces in real time a result like what you can see here. So it gives us the probability for the child to have normal or abnormal visual development. So in order to develop this, we could not, well, if you guys have learned a bit or have worked a bit with deep learning, artificial intelligence techniques, you know that data is very important. You need a lot of data in order to train our models. And in our case, we could not just download a data set from the internet because our application is very specific, and we had to do everything ourselves from scratch. So a very big part of our project was bringing our dive device to different countries and use it to collect data. So we were in Mexico, in Spain, of course, Russia, Vietnam, and China, and collecting data from many different children in order to train our model. And well, I will not be able to give you a lot of details regarding neural networks that we use because due to confidentiality reasons, but I can explain to you a little bit of the relevant parts that went into the development. So first, before I go into detail, I'm going to explain to you how we measure how good or bad a screening system is. So let's imagine on the left-hand side of my screen here, I have our test set. So I have a group of children that have abnormal visual development and a group of children who have normal visual development. And then we need to compute the sensitivity and the specificity. The sensitivity is the percentage of children with abnormal visual development that we are able to detect correctly. And the specificity is the percentage of children with normal visual development that we are able to detect correctly. So the ideal thing we would like to get would be something like this. So we would like to detect all children with abnormal vision as abnormal, and we would like to classify all children with normal vision as normal. And that would give us 100% sensitivity and 100% specificity. Now, let me tell you right now, this is impossible. This is impossible to get. There are way too many particularities in each person. I mean, we are real people. This is impossible to get. So our goal is going to be to get these two numbers as high as possible. And especially because we are developing a screening system, our main goal is going to be to make the sensitivity as high as possible, because we want to miss as few children with abnormal vision as possible, even if that means decreasing the specificity a bit. Okay, so going back to our recruitment, our data collection phase and so on, we were in all these cities, in all these countries. In each one of the countries, we had ophthalmologists that worked on site exploring vision in children in order to create our data set. So finally, we got a data set with more than 2,000 patients that we were going to use to train our AI algorithms. And our data sets, for each patient, we had the following information. So we have on one side, the visual exploration performed with DIVE, and we have that. And then on the other hand, independently, we had an ophthalmologist perform a full traditional exploration with the traditional methods, complete global visual exam, and then they produced a diagnosis. And this diagnosis is what we are going to use as labels to train our neural networks. So we had this, we had more than 2,000 patients. We were super excited to develop our screening system. We developed a first version of the neural network, a naive version at first, but we were super excited. We tested out right away and we got something like this. So this didn't look very, very good. Results were, well, this was more or less like randomly choosing if children were normal or not. So yeah, we had to look into things with a little bit more care. So we had to improve both the data that we had and the model that we had developed. And in order to do that, we focused on different things. First of all, we had to analyze the data quality. Sometimes data quality is bad because the patient has abnormal vision, so he does not look as accurately at things. But sometimes data may also be bad because the children did not pay attention, because they are children, they get distracted, because the eye tracking is failing, or because there's a bad calibration. And this is an ill-posed problem. It's very difficult to figure out which case it is, because you can have a bad calibration because it's bad calibration, or because you have bad vision. So it's very difficult. So we developed different metrics related to the quality of the data that we have. We tested how well those metrics related to our actual quality, and then we figured out the best way to input this information into the model so that it could learn from it. Another thing we had to do, well, actually, the ophthalmologists had to do this, was going through the patient sheets. So we called patient sheets to all the information of the traditional exploration and diagnosis that the ophthalmologist at each center had, each center had created and had registered. So before starting at each center, we created a very detailed protocol. We taught them how to follow the protocol, how everything had to be done exactly. Ophthalmologists from Spain traveled to all the different places and gave on-site training sessions to all the ophthalmologists involved in this project. But still, when we got the data back and started looking at it, we started realizing that some things maybe hadn't been correctly written down, or there were errors. So we had to check if ophthalmologists had done a good job at making the diagnosis that we are then going to use as labels. So the ophthalmologists had to go through the painful task of going through the 2,000 patients one by one, double checking if all the information was accurate, if things added up. They excluded lots of patients. They changed labels in some of the patients until we were sure that we had a database that was robust and that had correct information. Another thing we had to do is decide which parameters we should use as input for our model, because we can have dozens and dozens of parameters. There's a lot of information that we can extract from our DIVE explorations. And so we have to figure out what is the right amount and which parameters are key and should be input into our network so that we can get the best result possible. And there's also an additional important thing in here, because we are working with children. It's important to make the tests as short as possible. So in this particular section of the work, if we found there were certain metrics that were not as relevant, that were not giving us as much information, and if there was a part of the test that we could exclude, then that was super good news, because making the test shorter is a huge improvement for us, because children have a short attention span. Another thing that we had to take into account is age. Age is very relevant. When we are born, our visual system is in a very immature state, and it develops as we grow older, especially during the first years of life. So we had to feed this information into the model, because a 6-month-old baby with normal visual development does not look at things the same way a 6-year-old child does. So it was very relevant to put this into the model in the proper way. And then, after we had gone through all these improvements, what we are left with, what the neural network outputs, is a probability between 0 and 1. But actually, what we have to give back to the user is a classification. We have to say if the child has normal vision or abnormal vision. So we need to set a threshold in this 0 to 1 probability range. Naively, we could just set a threshold in 0.1. Anything above 0.5, I'm not sure if I said it correctly the first time. Anyway, anything over 0.5 would be abnormal vision. Anything lower than 0.5 would be normal vision. But we can do something more scientific in order to set the threshold. And that is using a ROC curve. ROC curves look something like this. What we have to do is we plot on the horizontal axis the false positive rate, so the amount of children with normal vision that we do not detect correctly. So in this case, we want to be as close to 0 as possible. And on the vertical axis, we have the true positive rate, so the amount of children with abnormal vision that we detect correctly. And in this case, we want to be as high as possible, as closest to 1 as possible. So we would like to be on the top left corner of the graph. Here you can see different examples of different models plotted in here. The best one would be the green one, because it's the model that allows us to be closest to the top left corner. And then how does this ROC curve work together with setting the threshold? So if we, for example, set a threshold up there, we set it very high, so that only, for example, values higher than 0.9 would be classified as having abnormal vision. That means we would have a very small false positive rate, but we would also have a very small true positive rate, which is not what we want. If we go to the other side of the spectrum, if we set the threshold very, very low, we would be classifying a lot of children as having abnormal vision. So we would have a very high true positive rate, but also a very high false positive rate, which is not what we want. The key is to find the perfect balance. So maybe somewhere around these lines, we would have a pretty high positive rate with not very high false positive rate. And that is what we want. And also remember, because it's a screening, we want to improve sensitivity. So we prefer to have a better true positive rate, even if that means increasing the false positive rate a little bit. So when taking all this into consideration, we got a result like this. So this, let me tell you, in case you're not sure, this is actually pretty good. We are similar to or even better than other screening mechanisms for different types of pathologies in the health sector. We are doing pretty good. And also, let me tell you, not even ophthalmologists can do this perfectly, because there are many borderline cases in which it is very difficult for anybody to just make a classification towards one side or the other. And actually, this is just the beginning. This is our first model, and we are just scratching the surface of all the possibilities that we have when applying artificial intelligence to detection of visual pathologies. For example, other things that we could do, we could apply it to the classification of gaze into fixations and saccades. So first, let me tell you what a fixation and a saccade are. Fixations are when we are looking at a small area, just fixating our gaze on a small area. So right now we are fixating, or this example, the person was fixating on each bee. And then a saccade is a rapid movement of the eye going from one point to another. So every time a new bee appears on the screen, there's a saccade towards that bee. So this classification is the starting point of lots of other metrics and computations. So it is very relevant to do it properly. And when seeing this video here, you may think it's not that complex. So you just get the bunch of gazes that are together, and that's a fixation, and you're done. But remember that we may have children with a gaze that looks like this. And our fixation and saccade classification needs to work for both cases. So you can see it is quite complex to do this. It's quite a complex problem. And one thing that we believe is going to improve our classification, and we're starting to look into, is long short-term memory networks. Because so far we are not taking the temporal domain of the gazes into account. But if these types of networks do take the temporal domain into account, and we believe it can improve immensely. Other things we can do, we can detect more things in regards to visual pathologies. Right now, we're classifying normal or abnormal vision, but we can also give indications of specific pathologies the patient may have. So we are already giving indications. We are already doing something, for example, related to strabismus. But this is also, we have a preliminary version, but it's ongoing work, and there are more things we can do with this. And also through vision, we can detect many other pathologies, not directly really classified as visual pathology. So for example, the way vision works can be a cue to detect autism or attention deficit disorders, or also in the elderly population, it can help us detect things like Alzheimer's or Parkinson's. So there's a lot of exciting work ahead of us that we are very, very excited to do. And another very interesting thing is implementing smartphone-only eye tracking. So if we were able to implement a good enough eye tracking system able to work only with the smartphone camera, that would open up a whole world of possibilities. Imagine using your smartphone only with your eyes. So you would have a lot of possible applications for that. And then when applying it in particular to our vision screening, it would mean making it truly accessible, much more affordable, much more portable, and it would make it so much easier so that we could bring it truly anywhere, any developing countries, any areas with difficult access. So this would be really, really huge. And this is something we're starting to work on. Okay, so far you've seen all the journey. We've gone through all the developments that we've done in order to develop a device that ophthalmologists could use to explore vision, then how we integrated deep learning into our device so that we could perform visual screenings. And now, as I told you at the beginning, we have finally founded a startup. So I will not get into the startup things because that could be a talk on its own. Just so you know, as I told you before, we've already achieved a lot of things. We have been finalists or winners of many different entrepreneurship awards. We've been invested in by some very big players. We're collaborating with Huawei. We are also able to travel to many different places in order to present our technology. For example, this image here is at an event in Shanghai. We've been to different events. Also recently in January, we were able to present our device in the World Economic Forum in Davos. And that also opened up a great opportunity for us because people from the government of Saudi Arabia saw our product and they got in touch with us because we are discussing the possibility of incorporating DIVE into the health system in Saudi Arabia. And in particular, this is in the context of NEOM, which I'm not sure if you heard about NEOM, but Saudi Arabia is building a city from scratch huge city. I think it's like 33 times the size of Manhattan. They are putting $500 billion into this, and it's going to be a city for 1 million people, I believe, and it is being designed from the very beginning to be the city of the future, taking into account all the latest developments in technology and in especially in what is relevant to us in health. So they want to put in here, they want it to be a hub of innovation and to test all the latest trends and all the latest inventions. So it is a very real possibility that Dive may be integrated into this city of the future in Saudi Arabia. So I think so far what I want to say, just to finish off, is that if you find this as interesting as we do and as exciting as we do, you should know that we are a startup located in Zaragoza, but with huge potential and a worldwide impact. And we are offering internships and TFM projects for you guys at the Masters. So if you are interested, you can contact me or Diego Gutierrez or Belén Maciá, who are professors at the Masters. And I'm sure we can work something out to work together. And I think that's it from my side.
Well, Marta, thanks a lot. That was like very enlightening talk. I wasn't aware of the outreach of Google too. That was interesting to hear. Well, welcome. I mean, she's welcome to answer questions now. So we have plenty of time for answering any questions. In the meantime, I don't know if we have some questions already. Yeah. So Carlos says, do you think you can get similar results with cheaper eye trackers, not necessarily with your mobile camera?
Well, but you mean for using it with a smartphone, or? So I can start elaborating, and then if they write something else, you can tell me. So we found out during all the tests we've been doing, we've played around with lots of different eye trackers. The price is not directly related to the quality of the eye tracking they perform. So first we were using eye trackers that were like 200 euros or $200, something like that, and they work really, really well. Then that company was bought off by Oculus. We had to change to a different brand, and we started using some eye trackers that costed 5,000 euros just for hiring them during 8 months. So you can imagine the difference, and they actually didn't work really well. And now there's a different technology. The ones we're using right now cost like 1,500 euros, something like that. So the price is not related to the quality of the eye tracking.
So there's another question from Diego Arroyo. Thanks for the interesting talk. You talk about eye tracker calibration. Is it necessary to calibrate the eye tracker for each patient or children? If so, what's the calibration process? And given that you cannot be sure about the possible conditions of those patients' vision.
Yeah, so the way the calibration works, it's we show stimulus in different parts of the screen. So, for example, 9 points uniformly distributed across the screen, and so because of preferential looking, the person, the user, child, whoever, is looking at each one of those points when they are on the screen, and so you are collecting the gaze information during that time, and you are computing or you are calculating what the shape of the reflection of the infrared light is in the eye of the patient while they were looking at the calibration point in the top left-hand side of the screen, in the center of the screen, in the right side of the screen. So then with interpolation, you can relate the shape of that reflection to any other point in the screen. It is better necessary to recalibrate for each patient, just because each one of us has a different eye structure, eye size, eye separation, and it is better to recalibrate for each patient. If you do not recalibrate, it will do something. It will use the previous calibration that it has stored, but it will not give you as high accuracy as if you recalibrate again. And the last thing this person mentioned, what do you do if, this person has bad eyesight, then they do not calibrate as well? Yes, that is a big problem. This is something we face all the time. So something we do, if we get a bad calibration, we instantly are on the lookout, because that right away could be a sign for bad eyesight. So that's something we do. We try recalibrating 2 or 3 times. If it still doesn't happen, it doesn't improve, then it's very probably linked to bad eyesight. But yeah, we try to get other signs of the quality of the data in order to figure out if it's actually bad eyesight or simply a bad calibration because the child looked another way.
Okay, we have another question from Javier Jimenez. Thanks for the talk. I see this device could detect so different ophthalmological problems, but my question is if there are any problem or kind of problem that I wouldn't be able to detect.
So right now, this device that is using the eye tracking is able to detect all the things, or well, with the tests we've developed so far, detects the things that manifest themselves at a distance of 65 centimeters from the screen, because that is the eye tracking distance. So for example, the device would not be able to tell you if you do not see something at 3 meters distance. So bad eyesight, like at a distance, that's something you cannot find out with eye tracking because you need to be closer to the screen. What we do in these cases, so for very young children, like 6-month-old child, if he does not have very, very bad eyesight at a long distance, then that does not manifest at 65 centimeters. So we would miss that. But we do include long distance tests for the cases in which children start to be a little bit older and they are able to start answering questions or pointing out at objects. For those cases, if at 65 centimeters you're still doing well, we will test the child at a longer distance if possible, and then see if we can detect that.
Okay, David Morilla, if you want to unmute the mic, you can ask yourself.
Okay, thank you very much for the talk. I have some questions. I would like to start with one, which is you collected a huge data set. Is it thought to be reutilized or sold to other companies, or is it only for private use?
So we are reusing it all the time. Data is one of our highest assets. So it's one of the most valuable things that we have. It took a lot of time to get this data set together, and it's also exclusive to our device, the part of the dive exploration, and it is also multi-ethnic. It has a lot of pathologies that we would not have been able to get if we had done this only in Spain, for example, because there are lots of things that children get treated for when they are young. But for example, we went to Vietnam and we saw a lot of pathologies that here we do not see anymore. So the data set is one of the most valuable things that we have. And we are planning on reusing it. We are using it every day. We are definitely not planning to sell it or make it public, because it's one of the things that makes us different. So it's a secret for us.
Okay. So another question is, during the last part, when you talked about classifying the different gaze processes, are also external stimuli considered? Like, for example, maybe one is like pointing to one object or moving from one object to another, but maybe one gaze is due to something on the sides, like happening outside of the screen. Is it also considered?
What we do, we cannot consider that because that's not something you can record on the device. You can only record what you're showing on the screen. So what we have to do is give very precise instructions of the environment in which the test has to be administered. So for example, it has to happen on a dark room. If the parent is in the room, it needs to be out of sight from the patient. You cannot talk to the patient while the test is going on. You have to close the door and put a sign outside so that there's no interruption. Things like that are very relevant. Also, we do detect if the child gets distracted and looks away from the screen, that we can detect. So what we do in that case is we stop the test, we launch a video with music that we've seen is useful to gather the attention of the patient back. And then when he looks back, the test resumes automatically. So what we try to do is avoid those distractions and try to detect when he's looking at other places.
Okay, and if I can do a small question related to the question from Diego about the calibration. Isn't it a problem that you're trying to calibrate a device with someone who could have abnormal vision, to test abnormal vision?
Yeah. It is a problem on itself. I don't have a straight question for this, because this is an ill-posed problem that is very, very difficult to solve. You have to distinguish when you have a bad calibration because maybe the eye tracker was failing at that particular moment. The patient looked away during the calibration phase for a few times. You have to distinguish when that happens from when the calibration is actually bad because the patient was trying their hardest, but they just couldn't see the stimulus. So yeah, there are not there's not a nice answer I can give you like, yeah, you have to do this and you're done solving your problem. No, there are quite a few metrics related to the quality of the data that you've gathered. We put them all together. We analyze them all in combination. We can check out how many times the child got distracted. We can check out the quality of that calibration, which we test right after the calibration is finished when the child has not had the chance to move a lot yet. We check if the child has moved a bit from his original position. There are a number of things we can check, but there's not like a clear, perfect answer.
Okay, thank you very much.
You're welcome.
We have another question by Diego Martinez. Have you considered using virtual reality resources as a virtual reality headset in order to do eye tracking and visual stimulations?
We have considered this. At a point, we did discuss this quite a few times. It's not something we are going to pursue right away, but we have it on the back of our minds, especially when exploring vision. There's one type of test, which is the visual field, which is meant to test how well you see like all around you. So specifically for that, VR would be ideal because it actually gets you on an environment in which you can test what anyone is seeing all around. So especially in that context, we have thought of VR for this. But remember again that we are talking about very, very young patients. So good luck putting a VR headset on a 6-month-old. So it is not something feasible for very young children. So that you get an idea, some very young children do not even allow the doctor or their parent to cover their eye with a patch in order to test the right eye and cover the other one. Some children, they do not even allow you to do that. So the VR headset for young children is not an option.
Okay, we have another question by Tomás Berriel. I would like to know what have been the major difficulties you have found working on a multidisciplinary team.
Okay, so I've been asked this a few times and I always answer the same thing. So the most complicated thing has been that we speak different languages. And I don't mean Spanish, English, and so on. I mean, we speak the engineering language and they speak the health language. So sometimes it's difficult for both teams to understand how much something takes for the other team, or if something is feasible, or if something is correct. So when we are designing, we work very, very closely together when we are designing the tests and developing everything. But sometimes for example, they will give us a certain set of specifications in order to implement something. We will implement it, and then they will say, I don't know, something as stupid as, but I cannot pause the test while it's running. And we're like, well, you didn't ask to pause the test. And they were like, they are children. They move around. You have to be able to pause. And we were like, well, tell me. I don't know if you don't tell me. So we had this sort of miscommunications, let's say, mostly funny. But yeah, it was until we understood the language each other used, and which things were relevant for the other, and which things were possible or not possible for the other. It took us a while, but yeah, it still happens from time to time, but we're doing better and better.
Okay, thanks. It seems, let me check. Carlos Bello says, have you already done any tests using an eye tracking only based on a camera's CV methods, computer vision methods, to estimate where the eye is looking at? Maybe it's not been possible at the moment.
What we have done, not with the smartphone, but with a camera, infrared camera located underneath the screen, which would be more like testing if we could build our own eye tracker, so that we didn't have to depend on eye trackers from other companies. We have tried that, and we got a good starting point. We would need to dedicate more time to that if we would want to use it for real. We got a good starting point, but it's not at the precision values that we would need in order to use it. And then regarding using it on the smartphone, we are starting to test it ourselves. Haven't done any proper final tests, but we have seen a few research papers that did that. Those research papers, so far as we've seen, they all also publish code and data sets. So it's something we could try fairly easily straight away, but they are not there yet. So there are some things out there, some mechanisms that have been tested, but it's still not good enough for us. Because imagine the size of a smartphone screen. If you get an imprecision only this big, then it's half of your screen. So you need very, very good precision. So technology is not there yet, but yes, that's something we want to test out because it would be huge to get it.
We have another answer by Pilar. Vidal, thanks for the talk. It was great. By performing tests in different countries or continents, did you find any relevant differences that were particularly helpful?
That were particularly
helpful.
We did not. One thing that we wanted to test if there were relevant differences with different ethnias, mainly because of the eye color. That's something that the ophthalmologist really wanted to check out. But then after analyzing the patients that they'd seen, we actually ended up discarding the ethnia as a relevant parameter. So it seems that there were not that many relevant aspects relating to vision associated to the countries or the ethnias. But the biggest difference we found was more sort of cultural, in the sense that, in Vietnam, for example, we got lots of children with very serious visual pathologies that here in Spain we do not see, because as soon as you detect it on a child, if he's 4 years old, 5 years old, 6, whatever, you operate on him and then the child's fine. But in Vietnam, they don't have those resources. They have very few ophthalmologists. So we, being at different places, gave us the opportunity to get higher number of pathologies that we would not have been able to get in developed countries. And also a quick funny thing, we found also cultural difference. Especially, I was told, I was not in Hong Kong during the screenings, but the colleagues, several colleagues of mine that were in Hong Kong, they would tell me that especially in Hong Kong, the children were so well behaved. They were like robots. They would sit in front of the screen. They wouldn't blink. They wouldn't move an inch. So they were a dream to work with, because normally children move around and sometimes you have to pause the test, restart it again. In Hong Kong, it was a breeze. They were like robots. So those are the main differences that we found.
We have another question from Jorge Condor, which says, a quick question regarding the possibility of bringing these devices' capabilities to a handheld phone format. Have you started considering how to control the variables that might be introduced with such a change, such as varying phone screen sizes, inclination of the device, distance of the device, camera positions, models of phones?
What I think we would have to do, so first of all, because you calibrate first, then there are a few things that get already automatically fixed with calibration. So if you place the phone a little bit higher, a little bit lower, a little bit tilted, that would automatically get fixed more or less with the calibration, because you would see specifically for that position and for that child exactly where the correct calibration for that specific combo. And that's also a problem that exists with our current device, because you can also sit the child a little bit higher, a little bit lower, put the device a little bit further away. So those problems already exist. I think what we would do in order to use the smartphone is maybe find a way, one of these arms that gets connected like to the edge of the table and grabs the phone like this. I think we would have to do something like that so that the phone could stand relatively stable during the whole test. I don't think it could be handheld. This is in order to do the screening or the testing. Then eye tracking in order to use your phone when you have it on your hand, that would be a different story, much more complicated.
I'm checking on YouTube, no questions on YouTube, and I think we're done. I had one question myself because I found it interesting, especially on the color science part and the color detection and all this dichromacy. I don't remember what's the exact name for that.
Dyschromatopsia.
Yeah, dyschromatopsia. Yeah. So I was wondering if you could, so you sort of place combinations of colors and try to detect which ones are not differentiable or distinguishable by the patient, right? Could you use that for building, first to triangulate that point that you were talking about that tells you what sort of pathology they have, but could you use those measurements or those data to build up a color space for that person? Because those are going to give you the points on the color space that you cannot distinguish one from another. Could you build up a color space? Because I know that many phones, especially related to phones, they allow you, there's some accessibility tools that allow you to change the color on the screen so you can distinguish things more clearly. It could be that a possibility, not only for diagnosing, but for creating like a personalized color changes on the screen.
Yeah, definitely. That's something we haven't gotten into, but we've discussed the possibility sometimes. So you could try to, because testing like the whole color space with great detail would take a lot of time, but you could take like the main lines and sample them like on different directions. Like we have like the main things figured out already. So you could make like a test as short as possible on the phone itself of the person and get a profile for them, a color perception profile, something like that, and then apply it to change the colors from two colors they do not distinguish so that they do distinguish them, and then they are able to have a better experience, I don't know, browsing the internet or watching a video or whatever. Yeah, that's definitely something doable.
Okay. And I have like another, that's just out of curiosity, does the luminance as well affect you, how much you... Because if you're used to seeing some colors in a brighter space or others, so I think it's more like a 3D space of chromaticity, which is sort of bidimensional in the space that you were talking about, and the luminance. Of course, luminance is going to help you to distinguish from some on others if the luminance is a contrasting factor. But sometimes maybe if you have more luminance, you can detect some colors better than others.
Yes. So what we do in order to make the test uniform and to have so that everyone can use it, and you get the profile for each person. We make let's see, the environment uniform, so everything's dark, there are no other sources of light, and then we also calibrate the screen so that you get the same screen brightness and all those things. We do that regularly, and so then from that, with the same screen characteristics, you display your stimuli. So the numbers you get for that person are with those specific screen characteristics and darkness in the environment and so on, so that then we can compare one person with another.
Okay, thanks. I'm checking if we have more questions. It seems that we don't have any either on Meet on YouTube, so probably we can wrap up here. Thanks a lot for the talk. I think it was pretty interesting, and I think the high-level concepts and also some lower-level, more technical details are very well understood. I think it was really interesting, and also the outreach. I think it's important that people know that this is reaching things like Huawei or Google, which are big names, and give us some hint on the quality of the research that we do. So thanks a lot, Marta, for the talk.
Great, thank you. Thank you very much for the invitation also.
And thanks a lot for attending. Now you should hear some sort of applause. I'm gonna start with this. Someone want to unmute the mics? Yeah, thank you. Thanks a lot, Marta.
Thanks. Thank you.
Thank you.
Thank you, Marta. Bye.
Bye-bye.
Bye.
Thanks a lot. Bye-bye.
Thanks. Bye.